Okay, uh, to design the circuit, now we have to first allocate some flip-flops to maintain the state of our states, right? So we have 4 states, and it is given here in the table that for each state what type of flip-flops or flip-flop values we can use. So there are two flip-flops, flip-flop A and B. So according to this configuration we can use it, right? It's just 0 1 2 3. You can follow the order, so it is easier. So there are different ways you can allocate the states to the flip-flops, but we will just use the simplest one for our uh, sake of simplicity. Okay, so now here is the state transition diagram we are trying to draw, and sorry, this is the uh, excitation table for our circuit, and this actually represent entire truth for our circuit design. So let's see how we can fill this one. Okay, so let's go ahead and try to fill this up. So there is I, right? Input I, current state QA, QB, right? So these are the current state, and we know that we can have QA t plus 1, right? QB t plus 1, and so this is the current state, this is the next state we are trying to achieve, and then we need uh, input signal or excitation signals for each of these uh, transitions to happen, right? So for QA I need two excitation signals, S and R, right? S and R. For B also I need S and R, two signals, right? So let's fill this up exhaustively so we know all the configurations possible. Let's go from 0 1 0 1 0 1 0 1 0 0 1 1 0 0 1 1. Okay, 0 0 0 0 1 1 1 1. So this is the exhaustive configurations of the entire circuit. And what are the transitions we can achieve or we need to implement in order to get the desired behavior of this particular state transition diagram? So that's the thing we are trying to uh, figure out. Okay, so as we allocated, S naught is going to be 0 0, right? This one 0 1 1 0 1 1, right? This is the order of q. You can determine what is the order as given in the document here. You can see state 1 QA going to be 0, and this going to be QB is going to be 1, right? Sorry, QA is 0, QB is 0, means S naught, right? So this is the order of this QB here, and this is QA here. Okay, so you need to make sure your order is correct, otherwise it will be a little bit complicated. Okay, so now it is out of the way, and we can fill up the table. Okay, how to achieve this transition now? So first we have to represent this state transition diagram in the table, right? We have all the configurations, so we know which one will be the next based on the state transition diagram. So if QA is 0 and QB is 0 and the input is 0, QA QB 0 means we are at state 0, right? And the input is also 0, so we are going to go to S1, right? So S1 is 0 1, right? So we can write here 0 1. Okay, nothing complicated if you just pay attention and carefully follow the procedure. So this is just cranking the lever, nothing much to do, just procedurally follow the instructions. Okay, now we are at 0 1 state here, right? then the input is 0. So we are going to 1 0. Okay, 1 0. Then we are at 1 0 and input is 0. So we are going to 1 1. Okay, from 1 1 we are going to 1 1. Input is 0. So we are going to 0 0. Okay. So now what is the situation if the input is 1? So you can observe here from 0 0. If we get input as 1, we are going to S2, right? S2 is 1 0. Okay. Input is 1 at 0 1. Now we are considering this state now. At this stage or state, if we get the input 1, what is the situation? This one, this transition, right? We are going to S3. So it will be 1 1. Okay. Again, we are considering another transition from 1 0 at input 1. 1 0 is S2, input 1 is this transition, so it's going to be 0 0. At 1 1, if there is a 1 as input, it's going to be this transition, so we are going to 0 1. Okay, it's just cranking the lever, nothing much to think about, so you have to just follow the procedure. Okay. So now we know all the transitions. This entire thing is represented in this table now. But we need to determine all the excitation signals. And we will be deriving the Boolean expressions for each of these signals so that we can implement a circuit accordingly. Okay. So to fill this up, we need the excitation table which we just derived before. So I will just copy it here so it will be easier for you to follow. Okay. So qt plus 1 is okay, 0 0 1 0 1 1. So what are the configurations? I'm just copying it here. 0x 1 0 0 1 x 0. Is it correct? Be careful and copy it correctly. So yes, because you will be using this table to finish up the entire table. Okay. So now let's see. Now there are two flip-flops, right? A is going from A, this is AT, right? If you just write it like that, AT and BT. AT is going, oh, QA is going from T to T plus 1, right? B is going from T to T plus 1. So what is the S and R signals necessary for that transitions to happen? That's what we are going to determine here. So let's consider QA here. Okay. So QA is going from 0 to 0. So you can refer here 0 to 0. S should be 0. R we don't care. Okay. So you can copy that row here. 0 don't care. You can follow the A first, then we can move to the B. 0 to 1. 0 to 1 must be 1 0. 1 to 1 is X 0, right? It's coming from here, right? 1 to 1 X 0. 1 to 0, 1 to 0 is 0 1. 0 to 1, 0 to 1 is going to be this row, right? 1 0. 0 to 1 1 0. 1 to 0 is 0 1. 1 to 0 again 0 1. Okay, so that's clear. Then now it's the S and R signals for SR flip flop A. Now let's consider the SR flip flop B. Okay, 0 to 1. 0 to 1, this is the same configuration for both, right? 0 to 1 1 0, 1 to 0 0 1, 0 to 1 1 0, 1 to 0, 0 1, 0 to 0, 0 don't care, 1 to 1 don't care, 0, 0 to 0, 0 don't care, 1 to 1, 1 to 1 is going to be don't care, 0. Okay, so now our entire excitation table is completed. Actually, at this point, your entire circuit or entire sequential circuit is reduced to a combinational circuit, as you can see, right? If you have this set of combinational circuit outputs, then you can plug this one into two SR flip-flops to get all the sequential behavior which we are expecting. So now let's try to deduce the Boolean expressions for all these four signals.